everyone. If we haven't met before, my name is Ben Wilkes. I'm the program manager for the TomTom Foundation. And on behalf of our board and our team, I'd like to invite you and thank you for being here. This morning's event is part of a 7-week virtual event series called the Cities Rising Summit. This week in particular is focused on programs around data and machine learning and is brought to you by S&P Global, who we thank for their incredible support and collaboration. All of Cities Rising events are on a pay-what-you-can scale and will be available on our YouTube channel. All talks will be recorded. The title of today's talk is Improving Your Data Visualization Flow with Altair and Vega-Lite, and features Rachel House of S&P Global. With that, I'm pleased to introduce her, and Rachel, I'll let you take it away.
Great, thanks, Ben. Share screen here. All right, and Ben, can you just confirm that we can see everything?
Yes, it looks good, Rachel.
Perfect. All right. Well, good morning, everyone. My name is Rachel House, and I'm a senior data scientist with S&P Global, and I'm super excited to kick off our day of Flash Talks today. And this morning, I'd like to talk to you about one of the important tools of our trade, data visualization, and how you can use Altair and the Vega-Lite stack to improve your own data visualization practice. Our time here today is short and sweet, so we're going to dive right in. Let's begin our journey with some observations about data visualization in the wild. We all know that A, there's a lot of data in the world, and that B, often to make sense of it, we need to transform that data from a non-intuitive representation to an intuitive representation. These things are not in question. We're all familiar with the usefulness and purpose of data visualization, which is why you're here today. Typically, we're concerned with two categories of graphics: exploratory and explanatory. Exploratory graphics are your quick vizzes that you like to make on the fly as you're exploring a data set. Explanatory graphics are those that are typically more thought out and used to communicate data findings with others, like your stakeholders. However, it's not always clear what processes or tools might be the most effective to get from data to graphic. Even within the landscape of a single programming language, like Python, there are a ton of options out there. And we all know that even after choosing a library, things can get very hairy very fast. Maybe you spend hours trying to figure out how to tweak a small but important detail on your graphic. Perhaps you produce a static image you're really happy with, but it's unclear how to add some interaction to it. Maybe all you want to do is recreate a graphic you've made before in the past, but some step in your 50 lines of imperative code is inexplicably now failing. I'm sure everyone's been here before, and it's a shame. It is a shame because data visualization encapsulates and exemplifies the disciplines of our field: data, analysis, code, design, and communication. And one of the true joys of our job is to be able to convey a data insight elegantly with a well thought out graphic. But we can't do that if the effort of wrangling a Python library eclipses the value of making the visualization in the first place. There has to be a better way. Which brings me to a discussion of the elements of a good data visualization flow. So what makes a good visualization flow? If the benefits of a good data visualization flow include efficient creation of visually appealing, insightful graphics, what are the features? Well, when I asked myself this question a couple months ago, I distilled my thoughts into what I consider to be the 3 essential tenets of any data visualization flow. A data visualization flow must enable you, the data scientist, the developer, the machine learning engineer, the technologist, to 1, produce visualizations quickly and intuitively. This includes exploratory and explanatory graphics. Ideally, we can accomplish this with a single tool, or a small set of core tools in which we are comfortable and confident. Visualization creation should be intuitive, with a clear way for you to express your graphic concept in the language of the tool. Second, we need the ability to easily create interactive visualizations. Interactive visualizations are here to stay. They're increasingly standard on the web and starting to gain a strong foothold in the business world. When interactivity can enhance an audience's understanding of your graphic and allow them to explore the data in a meaningful way, it's essential that you're able to seamlessly incorporate that interactivity. And third and finally, we need the ability to easily share and reproduce visuals. Reproducibility is the cornerstone of data science, and our resulting visualization should be no exception. Any data visualization flow worth its salt needs to preserve the data and the steps used to create a visual in a format that can be shared and reproduced by others. No more pings embedded within PowerPoint. So, these tenets sound refreshing but ideal, right? A bit of theory in a world of practice? Well, I have good news, everyone. A good data visualization flow that captures our three tenets is not only possible, but achievable. We're going to make these visualization dreams a reality. And since we're holding this talk virtually, it makes it really easy for me to pretend that everyone's on the edge of their seats right now, amped up about great data visualization. And even if you're not, get excited, because we're ready to move on to the stars of this talk, Altair and Vega-Lite. To understand Altair, it's first helpful to understand the tech stack upon which it sits, and we're going to work bottom up. So at the bottom of the stack, we have d3.js. D3 is a JavaScript visualization library, and it is what manipulates the actual HTML, SVG, and CSS in the web browser that renders your visualizations. On top of D3, we have Vega, a low-level declarative visualization grammar with a JSON syntax. Vega provides the building blocks needed to create an interactive visualization. It's kind of like assembly code, but for graphics. On top of Vega, we have Vega-Lite, which is a high-level grammar of interactive graphics that uses a concise declarative JSON syntax for visualization specification. Vega-Lite works by compiling its specs to Vega specs. And finally, at the top, we have Altair, which is a declarative visualization library built in Python. Altair essentially serves as Python bindings for the Vega-Lite grammar. I'm sure you all agree, that is one sweet stack. And Altair and Vega, pretty light too. So what makes this a really cool stack? Well, first, because it's all built upon D3, you're not tied to a particular framework or backend to render your visualizations. All you need is a modern web browser. This makes your work extremely portable and very shareable. Second, all visualizations created in this stack can be represented as a JSON specification that's interchangeable amongst Altair, Vega-Lite, and Vega. So if you're comfortable with JSON, and to some extent JavaScript, if you really want to delve into the guts of D3, you'll be able to tinker at whichever stack level you prefer. And finally, as Jake Vanderplas, creator of Altair, noted in his talk at PyCon 2017, Vega-Lite allows you to pass around visual specifications and data rather than pixels. And this capability is huge, like absolutely huge, as sharing open source specs and data rather than static copies of our visualization is precisely the sort of shift we need to improve data visualization reproducibility. Now that we've stepped through the Altair stack and its benefits, I'd like to dive in a bit further into the Vega-Lite grammar. You may have noticed the terms grammar and declarative bandied about in the last section. Let's take a minute to unpack what each of those means. First, a grammar of graphics is a tool that enables you to concisely describe the components of a visualization. Grammars of graphics provide mental models and building blocks rather than chart templates to create visualizations. The Vega-Lite grammar is declarative, which means that when using it, you can describe what you want to accomplish versus how the computer must accomplish it. And the resulting mentality is a much more natural language and human-based approach to thinking about and implementing graphics. It can be more intuitive than its counterpart, imperative. When we consider the differences between imperative and declarative approaches when it comes to making visualizations, there are a couple useful distinctions. The most notable is that an imperative style uses instructions on how to implement a graphic versus what to implement for the graphic. To help conceptualize this, compare writing a Python script to sift through and process data, which is an imperative approach, to writing a SQL command to query that data directly, a declarative approach. Typically, With an imperative approach, you need to manually specify each step required to create a plot. Whereas with a declarative tool, appropriate steps and details can be determined by the system based on your specification. And with a declarative grammar, the specification of the graphic can be separated from its execution. What this comes down to is that when creating data visualizations, we want to be able to focus on data and relationships and not battle with syntax and libraries. So declarative grammar can be a very powerful tool. And we all know talk is cheap. So let's look at some actual Vega-Lite. So as we load this, there we go. So what we have here at the top are some of the building blocks of Vega-Lite. First, we'll look at data, encoding, and mark. We have the Vega-Lite spec on the left here and the resulting visualization on the right. To visualize data, you first need the data itself. You can see here in the spec that we've included the data directly. Note that this is only one way to accommodate data with a Vega-based spec. It's also possible to reference a URL that serves out your desired data. And this is useful for large data sets when including the entire data set in plain text in the JSON file would result in a way too big spec file. Secondly, we need to determine the encoding of the data, namely how we map properties of the data to the visual attributes of the plot. The encodings we are using here include the x-axis and y-axis values. You'll also note that we've included the data type in our encoding, nominal for our column A values, and quantitative for our column B values. And lastly, we've specified the mark of the data as a point, which Vega-Lite defaults to a little empty circle with a border, seen here in the rendering. The mark property specifies how to represent mapped attributes on the plot. With Vega-Lite, you can also include data transformations and chart customizations in your spec. Here, you can see that we've used an aggregation function, the average, to encode values for the x-axis. Further, we've introduced a chart customization. Here, just a little change of title to get really excited about the mean. When we take a look at our Altair code, we'll see more extensive chart customizations, but I just wanted to include a small example here for Vega-Lite. This is pretty nifty. Vega-Lite offers an intuitive interface which you can use to quickly create visualizations by assembling graphographics-based specifications. Sweet. Well, let me tell you, we haven't even gotten to the best part yet. What is the best part? It is that in 2017, the Vega-Lite team introduced a grammar of interactions in Vega-Lite. This means that now interactions like mouse over, pan and zoom, interval selection, and brushing are built-in first-class citizens of the grammar. No more kludgy solutions to add interactions to your visualizations. There is support for these interactions directly in the grammar. And let me tell you, it's pretty awesome. Here, once this loads, there we go. Here we have a very simple mouse over selection defined. Get the real estate right there. We've named this selection, we've defined PTS, and it's just going to be a single data point selected on mouse over. When we take a look at our color encoding for this chart, we can see that it includes a condition which is tied to that PTS selection. If the select is active for a particular data point, we're going to show its appropriate color based on the aggregate count of records. And if it's inactive for a given data point, we're just going to color it gray. And we can see it here in action as we mouse over these points. Color for an actively selected mouse over and gray for the inactive. And one more small note on this example. Earlier, I mentioned that you can include data in a spec via a URL. And this is an example where we are pulling the Vega cars data set via a URL. In this example, we have a brush selection on the top chart, which controls the data points shown on the bottom chart via a filter. So we can see our brush selection here, and it's tied to the transform on the lower chart. So when we brush select over the top, the data that's shown on the bottom is controlled by that selection via a filter. At this point, I think we can say with certainty that Vega-Lite enables the easy creation of interactive visualizations. However, also at this point, perhaps you're thinking, Vega-Lite seems cool and all, but I'm not into editing JSON files. No way. Never fear, because with Altair, you will be able to reap all the benefits of the Vega-Lite grammar. And with that, it's time for our Altair demos. I'm going to switch over to Streamlit and we'll take a look at some code and visualizations. So for our demo today, we'll use S&P Global market data from Snowflake's cloud data platform and Altair to put together an interactive plot of stock price history for the NASDAQ Titans: Apple, Amazon, Microsoft, Alphabet, Facebook, and Tesla. These 6 tech stocks currently constitute about half of the index, or half of the value of the index, rather. But first, we'll have a quick word today, since this talk is sponsored by S&P Global. Let's talk about the data we're going to use. So S&P Global offers a wide collection of traditional, financial, and alternative data sets through its marketplace. And it's recently expanded those data offerings to provide select data sets through Snowflake Cloud Delivery. This allows you to get S&P data faster, reduce data transformation needs, improve operational efficiency, and directly integrate data into your existing tools and workflow. Now to the code. We'll import Altair here as alt for use below. And also, as I mentioned when we looked at the Vega-Lite specs, when you have a large amount of data you're working with, it generally makes more sense to include that data via a URL rather than plain text in the spec. So to accomplish this for our data today, because we have significantly more than 5,000 rows, we're going to use the Altair data server, which is a transformer plugin for Altair that just transparently serves your data for Altair charts via a background server. Really easy to use and really useful. Our first step in this demo is going to be to download the data from Snowflake. We'll use the Snowflake connector from Snowflake's Python library to establish a connection. I have my account details specified here, as well as the desired database to use. However, since the focus of this demo is Altair, I'm not going to spend too much time on the query itself or the data cleanup. But when we look at the query, let's just see, we're going to pull some relevant data for our tickers of interest, which are the NASDAQ Titans I mentioned earlier. And Snowflake's connector allows you to pull this data directly into a data frame, which is super handy. So you can see here, we're just doing a fetch pandas all. For the data cleanup, what's relevant here is that we're going to confine our data date range from the beginning of 1996 to today. Not much activity before 1996 for these guys. And we're going to narrow down our data frame to the columns of interest, including the stock ticker, the stock price date, the adjusted closing price, and the shares traded volume. Also, for the purposes of this demo, I've defined a couple constants and objects that we'll use for the downstream charts. This just includes dimensions, height and width, a shared Altair color scale that we'll be using, as well, or that we've tied to the unique ticker symbols of our data set, and then also the date range I just mentioned from 1996 to today. All right, so first, we're going to create a simple multi-line chart to visualize the history of stock closing prices by ticker. And you can see here that we're using the 3 building blocks we talked about for Vega-Lite: the data set, the mark, and the encoding. To create our chart, we simply instantiate an Altair chart object, so alt.chart here, and supply it with the data set, which we have as a pandas data frame. You can then set the mark with mark line and the encodings with encode. And you can see here how simple it is to designate your encodings. We have the pricing date encoded as the x-axis value, the closing price as the y-axis value, and the ticker symbol encoded as the color. And in our resulting plot, we also have some nice default aesthetics, complements of Altair. Now that we've created our initial exploratory plot, let's add some chart customizations. A plot title can be added by simply adding a title to the chart objects. So here we have our Titans of the NASDAQ. And then, let's see, To change the plot size, all we need to do is tack on a dot properties to our chart object and feed it our specified dimensions. And then for the color, we're just going to use the color scale that we defined in the section above, setting the scale to that color scale so that we can assign a distinct color to each ticker as well as ensure consistency for the rest of the demo. So you can see results here. Next, we're going to add a couple more detailed customizations. First, we're going to update our axis titles for the X and Y axis. And for the X-axis, since we're dealing with a time series, we're going to drop that default price date label supplied by Altair because it's pretty intuitive that we're looking at a time series. So to do this, we're just going to supply an Altair axis object to the X encoding with a title of none. And for the Y-axis, we have something pretty similar, just passing that axis object in, except for here, we're going to format our Y-axis values as a dollar currency. We're going to stick on a title, adjusted closing price, and give a little visual space between the title and the axis with the title padding. And to update the legend, we'll follow a similar pattern with the axis updates and pass in a legend object here that specifies the desired title of stock ticker. So, results. At this point, we're ready for our first interaction. Super excited. So including zoom and pan is a pretty standard and popular interaction. So Altair has made this as easy as appending a dot interactive to the end of your chart object that we can see here. With the chart defined as interactive, we can zoom and pan easily. So here, just scroll in and out for my zoom, and then click and drag for the pan. And one nice little touch that really pleased me about Altair when I first started using it is how smooth this value scaling is by default. I mean, everything's in the details, right? So as we scroll in, you can see we go from whole dollars to dollars and cents. If we get in really, really close there. And for the time scale, we zoom down from years to months to days to hours to specific timestamps. And it's all pretty seamless. So I thought that was super neat and worth noting. All right, so next we're going to take a look at a more customized interaction. Let's say we wanted to be able to click on a given stock ticker, like one of these guys up here, and then isolate that data on the plot. So we only want to see data for Apple or Amazon or maybe Facebook and Google at the same time. So to do this, it's really simple. First, we're going to define a multi-selection above our chart. This multi-selection, which we've named ticker selection, is tied to the ticker symbol field and bound to the legend. And once we've defined this interaction, we want to enable it on the chart and use our selection to filter the data that's displayed. To do this, all we have to do is add a dot selection onto our chart object, which enables that selection on the chart, as well as a dot transform filter, which is going to take the selection and then transform the chart data according to what you selected and filter it appropriately. So minus the white spacing and new lines here, for kind of visual code display effect, we're really only looking at about 3 lines of code to define this interaction, with a very straightforward way of defining how that interaction affects the plot. And when we take a look at the results, we can click through and see, oh yes, isolated data. And though you can't see this on my screen, if I hold down Shift, you can select groups of tickers at a time. And then if you double click outside here, it'll just revert you to your default state. So pretty neat. Next, we're going to create an additional plot. And this plot's going to visualize the trend in volume of shares traded for our 6 tickers. Our Altair chart definition is going to look a lot like the stock prices chart, and there's just a couple differences here to note. First one being, instead of a line, we're going to use an area mark and give it a little bit of transparency so that when we have overlapping volumes, we can see both of them. We've defined the limits or scale of our x-axis to be that date range from 1996 to today. And we've done a slightly different customization on our y-axis and removed the grid, the tick lines, and the labels. So here's our resulting chart. And you can see here we've also encoded the tickers using the same color as our other chart to maintain consistency. Now that we've created our shares traded volume plot, let's combine it with the stock prices plot and tie both charts to the same ticker selection so that we can also isolate data on our shares traded volume plot. So for this kind of iteration of chart evolution, our stock prices definition has not changed. That remains the same. All we're going to need to do to add the selection for the volume plot is to pop on a dot transform filter supplied with that ticker selection. And to combine the two charts, we're going to vertically concatenate them using the Altair shorthand of an ampersand. So here we have our two charts together, and you can see when we click on our tickers, we're getting that visual isolation or the data filtering for both of the charts. And same goes when we do a multi-select here. So really cool. We can examine the trend in stock price history as compared to the trend in shares volume at the same time for whichever selection of the NASDAQ Titans we prefer. And then let's add an additional interaction that allows us to select an interval in time that we would like to showcase on the top plot. We'll define our selection interval on the volume plot below, which will control the time range. So to do this, we'll define a new selection, time interval selection, which will be a selection of type interval and encoded to the x-axis. And to enable this interaction on the volume plot, we're going to use the dot add selection. Here we go. And supply it with our new time interval selection. To affect the stock prices plot, all we're going to have to do is to add a scale object to the X encoding that ties the domain to the selection. That's it. A couple simple changes. And now let's look at the result. All right, so in our resulting chart, we can select an interval of time on this bottom plot and see it reflected on the top chart. Pretty cool. But also note that the interactions here are layered, meaning that it's still possible to use our ticker selection while at the same time using the time interval selection. Really cool. So this is just a small taste of what you can accomplish with Altair. And I encourage you to check out the Altair docs. They have a great example gallery that showcases more interactions, customizations, and plotting possibilities than we have time for today. And with that, we're going to hop back to our slides. We've barreled through a lot of content in our short time together today. So I'd like to take a minute here to wrap up some of the important points from today. The Python visualization landscape is really diverse, and there's many excellent libraries out there that meet an array of use cases. It would be extremely short-sighted to crown a single option as the one visualization library to rule them all. However, I contend that making Altair and Vega-Lite the backbone of your data visualization process will enable you to achieve the following in your work. Intuitive, quick creation of both explanatory and exploratory graphics, easy generation of interactive visualizations, and reproducibility of shared visualizations. And with that, I'd like to say thank you very much for your interest and your attention and for coming to my talk. It's really been my pleasure, as always, to wax poetic about data visualization. And I hope that you've learned some new things or are excited to give Altair and Vega-Lite a try. And note that if you check out these slides online, and I think the link should be posted in the chat on this meeting, I have a resources section after this slide where I've listed some sites, papers, and talks that fueled this presentation. And so the final word being, go forth and visualize. And thanks again.